Today we shall discuss networked embedded system. The embedded systems, when they are networked, they actually provide us a distributed computing environment. Now, how these embedded systems can be networked, and secondly, what kind of applications we should look at for designing this kind of a networked embedded system based design. That will be the concern of our next few lectures. So, when shall we go for distributed embedded system? When processing tasks are physically distributed, it's an obvious choice, because the time constraints may not allow us the transmission of the data from the sensors to the central site, and therefore, we would like to do the processing at the node itself, sensor node itself, and then communicate maybe the process data to a central node, or may communicate the process data among these nodes which are physically distributed. Therefore, depending on the requirements of the problem, we may need to have distributed embedded system. The other interesting thing is that when large systems are assembled using existing processing elements, okay, so there are individual multiple processors are being used, and even in SOCs, today the trend is to set up a network among the multiple processors which are being used on the same SOC itself. So, you have what is called network of processors. So, that is another reason for going for networked embedded systems. One obvious consequence of networking is improved debugging, because you can use one CPU or the system in the network to debug others. So, what kind of architectures you expect for distributed embedded systems? Obviously, a set of processing elements would be connected via a communication link. These processing elements may be DSP, maybe a microcontroller or an ASIC, even it can be an ASIP. Also, there would be sensors and or actuators. All these things would communicate based on a protocol for communication, and there would be a different topology with which these elements can be connected. And unlike buses, we have already discussed buses, some of the buses also have various kinds of protocol based features. Unlike buses, the protocol machine is typically implemented in software in these networked systems. Although when we are talking about implementation of the software, we are not eliminating the possibility of having hardware support to implement such software. And the most importantly, such network processors will not have shared memory. This is the most important distinguishing feature when we say that assertive processors are connected via bus or they are connected via network. So, typically a networked system would look something like this. These are all processing elements. This is a communication link. This is providing the basic network backbone. There are these actuators which are connected to the processing elements. There are the sensors connected to the processing elements, and there could be a standalone processing element as well. And when we are talking of the network, this network base is actually may consist of hardware elements as well. And those hardware elements, by the way, are also embedded systems. So, for example, if I consider a router in a network, that itself is an embedded system. So, P's may be CPUs or ASICs as the case may be. Now, networks obviously are therefore complex systems. So, we need some mechanism of abstraction. The most common abstraction is the one which was proposed by ISO and known as Open Systems Interconnection Model or OSI model, and that is a 7-layer model, and it provides a standard way to classify network components and operations. So, the basic model consists of what we say the physical layer, which talks about the mechanical and the electrical signals that would basically be communicated among the processing elements. Data link layer, which enables reliable data transport, error correction can be part of data link layer. Network provides end-to-end service. Your transport layers actually provide from end-to-end connections, that is from source to destination connections is provided through transport layer. You have the session layer, which is on top of the transport connections, managing the application dialog. You have got presentation layer, which is more concerned with data formats being exchanged, and on top you have got applications which enable communication between end user applications. So these are the 7 layers as part of OSI model. So several networks and network protocols that we shall look at, they will be implementing some parts of the layers. It's not necessary that they will implement all of these layers, and depending on the layers that they implement, the applications may be built on top of them. So going back to that OSI layer definitions, what we say, the physical layer handles transmission of raw bits over a communication link. Data link layer collects a stream of bits into a larger aggregate called frames. And error detection and control across a single link is typically the management of data link. So it is what we say a single hop, because the data can go from one point to another point, that is between source to destination, via multiple hops. Network layer handles routing of packets among nodes, okay, and it therefore manages end-to-end multi-hop data communication. Transport layer provides end-to-end connections, okay, that is it maintains the connections between your source and destination independent of the fact how the network layer routes the data from one point to another point. And it would look also at optimizing the network resources. Session layers provide services for end user applications, data grouping, checkpointing. So if there is an error, it can identify that error through some synchronization points, and so that there can be resynchronization of the data. Say for example, when we talk about grouping of audio and video data in a teleconferencing or a video conferencing application may be transported over 2 distinct transport links, and the session layer's responsibility is to group the data and present it to the user appropriately. The presentation layer is concerned with data formats and transformation services. Say for example, formats of integers can be different over different machines. One machine can be big endian, other machine can be small endian. How 2 such machines communicate so their interpretation of data is consistent, that is taken care of by the presentation layer. An application is interface between network and end user programs. The most common application layer protocol that we use even in the context of embedded systems is your HTTP protocol, hypertext transfer protocol. And the architecture, if you look into for communication, this may be an end host, okay, these are the 2 end hosts, and then it goes through network. So these network these layers, that network, data link and physical layers, can provide the communication path, and this transport layer maintains actually this end-to-end connection, and the session presentation and application provides a top layer services for this kind of network communication. Obviously this is a complete conceptual model, okay, actual implementations would have specification of definite protocols. So what is the basic system architecture? Distributed systems are therefore organized in different ways depending upon needs of applications as well as cost constraints. And these networks, although we talk about this as a basic protocol model, OSI model as a basic protocol abstraction model, networks can be classified based on scheduling of communication, topology that they follow and the routing strategy that are adopted. So the simplest network that we can have is a point-to-point networks. There is one source and one destination and there is no data switching. So if we are building a network over the serial port between the P's, we shall have this kind of a point-to-point network connection. It can be a full duplet or half duplet communication. The other thing is that bus, we have already studied bus based communication, but here what we are talking about are bus based networks. So obviously the basic distinction with the other buses that we have considered so far would be that we shall not be expecting any shared memory lying on the bus or connected to the bus to which the PEs would communicate. So, there are multiple processing elements, okay, which are connected on the bus, okay, and the data which is being transmitted are typically divided into packets. So, you will have a typical packet format, okay. So, this packet format will have header, address, data and basically error correction code. Now, this address would tell possibly PE whether this data is meant for it or not. So, effectively the data would flow on the bus. The bus is common among the processing elements, and depending on the address a processor would know whether it is intended for it or not. Obviously, in these such cases arbitration, just like in any other bus, like a typical processor bus, the arbitration here also is of importance. So, you can have similarly fixed arbitration, same order of resolution every time, or you may have a round robin. If it is a round robin, we say a fair, because every PE has same access over long periods. So, here is an example. If I have a fixed priority at 2 points, always you will have A, B, C. If they are requesting, the priority will be assigned A, B, C. Now, if it is a round robin, since B has been assigned the second priority, the second time when there is this request of data transmission, B would get the priority and A's priority would be last. Okay. So, here the basic point is, at this point if both A, B, C, that is all three processing elements are trying to transmit the data, there has to be an arbitration scheme, and that arbitration scheme would resolve in favor of the priority. Okay. If it is a fixed priority, the highest priority system always gets preference. If it is a round robin, the priority changes dynamically. Now, how this is a bar, basically the bus connection. The other possibility is a crossbar. Crossbar enables all possible communication paths between the processing elements. So, it reduces, that is why we say communication conflicts of bus based connection, because in a bus based connection there can be always a conflict, and so we need a priority scheme to resolve these conflicts. And crossbar allows all possible input output connection, and typically that network is built around a cross point, which is a switch that connects an input to an output. And it is a non-blocking, that means if a data is requested, okay, or the data is being sent, what happens in a non-blocking case? The data becomes available, so the processor is not waiting for getting a chance to transmit or getting a chance to receive, and can handle arbitrary multicast combinations. If you look at a bus based configuration, multicasting would require what? Multicast means the data meant for multiple processing elements. So, you have to use some special address. If it is a broadcast, there also you need to use some special address. Okay. Otherwise, the processing elements would not know whether the data is meant for it or not. But here the combination is such, you can have, depending on the connection pattern, you can have multicast as well as broadcast combinations. And the size is proportional to n square. Why n square? It will be clear if you see the basic conceptual note. So, here if these are all, if you see in 1, in 2, in 4 and out 1, out 2, out 4, these are input and output lines, and this is a cross switch actually, this is a switch, and this switch you can realize that can establish connection between any input point to any output point, and there can be multiple connections simultaneously being set up. So, if I put this switch on, effectively I get this input 1 connected to output 2, and this input and output are what? Basically the ports, the connection ports on the different processing elements. So, you can have any possible combination of input output. So, in fact, data from processing elements, processing element 1. So, data can come to processing element 1 from, here say processing element 2, but at the same time if I enable these switches, the data from processing element 2 can go to both processing element 1, maybe not 2, 2 is part of the processing element 2 itself, to 3 as well as to 4. Okay. Obviously, the complexity here is n square. In many cases, actually if you are looking at SOC based implementations with multiple processors. If there is a demand of this kind of communication, you will find these cross-bus switches being implemented in the silicon itself. The other standard topologies are, one is, this is typically a ring. So, the processing elements are connected via ring. This we say a repeater, that means once it gets data, okay, from the station, the repeater basically reinforces the data so that it can be moving around in the network. Okay. The basic difference here with respect to the bus is just in terms of the connectivity. Okay. Otherwise, here also all these stations are listening to a common link. This is a tree structured connection where you have the different links, in fact multiple buses, and being managed through a head end. This is a star link. So, you have a central hub or a switch or a repeater to which individual stations are connected. Now, obviously, you can understand if this hub fails, the networks become completely disconnected. Okay. Now, these hubs themselves have to be satisfy the basic condition of switching packets or the data from one source to another destination in a pretty fast way. And in fact, if you see your cross-bus switch, if I use it here, I get therefore all possible n square connectivity between the nodes. There are also multi-stage networks, because networks can have different capabilities. Okay. So, if you have networks with different capabilities, and that is also application dependent, because you may like to segregate critical and non-critical communication tasks into two distinct networks. Okay. So, if it is into two distinct networks, you may use different switching elements in the network base itself. This is a basic network connectivity, that is connectivity matrix. So, you can use different kinds of switching elements, and these switching elements actually would enable communication if required between the parts of the network, okay, that is between individual processing elements or between the complex network. So, the basic difference with the crossbar, what you find is, obviously it is much less, because all possible connectivity is not being provided. You are providing selective connectivity using selective use of your switching elements. So, you effectively get a multi-stage network, and these networks can operate for different requirements, operate to meet different requirements. Maybe there is a critical communication requirement between these two processing elements. So, this is all connected via this switching element, and that is not true with respect to this. So, this processing element is not connected through this. Okay. So, if at all the connection has to come from here, it may have to take a complex path, okay, and the time required for a data to arrive from this processor to this processor would be more than between these two processes. Okay. So, effectively I am taking care of the need of the communication tasks and accordingly using the switching elements. Now, obviously, in this kind of a network, since you do not have a shared memory, how do the tasks communicate with each other? The basic way for such communication would be messages. So, embedded systems in such cases would communicate by passing messages. And the transport layer in the OSI model provides the basic message based programming interface, and typically a message must be broken into packets at the source and reassembled at a destination. So, this is the basic feature of a packet network, and each packet can follow a different path. And what we say, the basic programming model wise, that this is data push programming, make things happen in network based on data transfers. That is, when you get a data from a sensor, then some action has to be initiated. So, that becomes what we call data push programming style of application development. Let us take an example. So, this is example of a car. Okay. Now, the car can have a multiple sensors, car can have multiple actuators. So, if you see here what we have shown, there is a front impact sensor. If there is an accident, a front impact sensor. You have got the brakes, which are actually, if you remember, we had actually discussed brake control system. So, these brakes, they can be controlled with regard to this controller. Okay. Then you have got the side impact sensors, you have the main controller, and you have got also the engine, which has also been controlled by a microcontroller. So, you will find that so many sensors and so many processing elements are existing in this car, okay, and they need to be connected together. So, what is the best way to connecting them together would be a network, okay, and in that such a situation you will find that these sensors would transmit data automatically at regular interval rather than the controller requesting for it, okay. Because if I have to take some action, it would be on the basis of what happens. So, if you take a look at an extreme case, so if there is an impact, so front impact sensor would send, because there is a P attached to the sensor as well, that will send the data to the controller. Controller in turn will trigger the engine microcontroller to stop the ignition, okay. So, it is not a request based transfer, but it is an example of a data push programming, that is whenever something is happening, the message is being passed and message is triggering the controller to take action, okay. So, the whole style of programming or the application development in such a scenario would be different. Now, what we need to look at is, if such a network has to be built, do we need to have some spatial requirements? Now, obviously you can understand that if we are looking at this kind of an appliance, say a car, where we would like to have such multiple processing elements to be networked, we may not need, and we do not need all 7 layers of OSI model to be implemented, okay. So, what we shall have? We shall have a subset of such a model with special emphasis on the requirements of such a system. So, such protocols are primarily intended for this kind of embedded applications. So, one such protocol we shall look at now, control area network protocol. In fact, this control area network protocol was developed for catering to requirements of automobiles, the example that we had just seen. So, it is a specification for serial network, okay. That means basic communication is a serial link based communication. It is an ISO standard and used in embedded systems for the network established among microcontrollers. And you have seen in a car, there would be microcontrollers associated with the various sensors as well as the main controller. So, how to network such microcontrollers? It is a two-wire half duplex high speed network system and is well suited for high speed applications using short messages and not really long data flow. So, you are not expecting a continuous long stream of data being exchanged. So, CAN is used, we shall see later on also many more applications, industrial automation, automotive, that is the car, home area networks. And CAN standard basically specifies physical layer and data link layer. So, if we look into it, so these parts are defined by the CAN protocol and these are part of higher level protocol which may be implemented by a particular manufacturer. Okay. Say for example, if I have these two specifications available with me, so what happens? I can use components as well as CAN controllers from variety of sources because they will be all compatible with these two specifications. Just like today you can buy an Ethernet card for your PC from a number of vendors because all of them are consistent with respect to that standard. Similarly, you can have therefore CAN protocol consistent components for these kind of applications and say a particular car manufacturer, okay, they can have a kind of higher level protocols implemented on top of these two layers. And they need not implement all these layers, okay, they would implement some of the functionalities that are required for them. Now, this model is something which is very important for you to understand when you are talking about networking embedded systems. You really do not need always the full-fledged functionality of all OSI layers. Okay. Wherever the functionality is needed, you need to exploit them. These functionalities may be application specific and some part of the functionality can be standards based. So, here for CAN, data link and physical layer are the specification of the standards, remaining can be purely application based. So, basically obviously if we are looking at this kind of a network, there would be transmitter and there would be a receiver. Transmitter is a node which originates a message, because this primarily I am sending messages, and that is exactly the model that we have looked at for implementation of such a system. And the message remains, any node can start transmitting the message if the bus is free. So, the transmitter waits until bus becomes idle or loses the arbitration. A receiver, a node is called a receiver if it is not sending the message and the bus is not idle. So, in fact, in a way you can see that each node can take up the functional role of a transmitter or the receiver depending on the need. The messages are nothing but information on the bus that is sent, and they are typically fixed format messages of different but limited length. Okay. Now, obviously, if you remember when we say data link layer protocol, data link, the basic task of data link is to define this kind of frame. So, that data link layer functionality is coming in when we are defining a structure of such messages. And there would be a message routing, because messages are meant for different processing elements. So, each message is named by an identifier. The identifier does not indicate the destination of a message, but describes the meaning of the data, so that all nodes in the network are able to decide by message filtering whether the data is to be acted upon by them or not. So, effectively if you see, what we are talking about is that a connectivity structure where all nodes are listening to the messages being transmitted on the link. Okay. So, it is similar to your typical bus based network. All of them are listening to data which is being transmitted to the link, and depending on the identifier, a node decides whether some action has to be taken or not. Okay. So, automatically your multicasting, broadcasting is built into this kind of scheme, because it is not just based on the address, it is based on the identifier which actually indicates the meaning of the data, based on which a node decides to act. So, multicast is as a consequence of message filtering, any number of nodes can receive and simultaneously act upon the same message. This is the most important feature. Okay. So, multicasting becomes automatic. And obviously, I need a priority, because if all of them are listening, there will be always conflicts if more than one node is trying to transmit data. So, I need a mechanism to resolve this conflict, and here again the priorities are used. The identifier defines a static message priority during bus access. There are also mechanisms for requesting for data. Okay. A node requiring data may request another node to send the corresponding data frame. So, if you see that there are two kinds of messages actually we are talking about. One message is that of sending the data, another message is that of requesting the data. So, a transmitter can actually send data, or it can also send a request for data. Arbitration occurs when two or more units start transmitting message at the same time, and it is resolved by using the identifier priority. The mechanism of arbitration guarantees that neither information nor time is strictly lost. Okay. So, that arbitration mechanism is an interesting part of CAN, and we shall discuss it later on. First, let us start looking at the physical layer. Okay. Physical layer is it suggests the transmission of the data, okay, in a differential mode. That is, it is a two-wire CAN bus. So, we have what we call CAN high and CAN low lines, and two wires operate in differential mode. That is, they are carrying inverted voltages. Okay. So, why differential mode? The advantage is there will be a automatic noise cancellation. Okay. And if you are looking at an application scenario of that of a car which is highly noisy than that of any standard networking environment. So, if we have a differential mode, then the noise cancellation becomes much better. Also, optical fibers have also been used, which is naturally protected against this noise. The other interesting feature of the physical layer is must support what is called bit dominance, and in this case the low bits are always dominant. That means if one node tries to send a low and another node tries to send a high, the result on the bus will be a low. Now, this is very similar to your I2C bus configuration. So, CAN physical layer would be something like this. So, you have got the CAN transmitter and CAN receiver data lines. This can come from a CAN controller. This is your differential bus driver, and that will be connected to a twisted pair, because I can use a twisted pair cable for differential mode transmission. So, that will be connected to a twisted pair cable. If we are using an optical transmitter receiver, that will be connected to an optical fiber. So, both these are being used with regard to the CAN, and these lines would communicate with the CAN controller. And bit dominance basically tells you the basic combination. So, if it is effectively what? A wired AND function. So, the basic connection mechanism can again be implemented through a simple wired AND. Next comes the bit encoding, okay, because at the bit level how the bit information is encoded. Typically what is used is non-return to 0 level. This is a standard way of sending digital data, non-return to 0 level. There are two different voltages for 0 and 1, and voltage is constant during bit interval. So, no transition, so that is no return to 0 voltage, and absence of voltage for 0 and constant positive for 1. There could be other way around also, more of a negative voltage for one value and positive for the other. So, there can be any way around, but what is important is that there are no transitions. Okay? So, the bit period, so what is important to note is voltage constant during bit interval. There is no transition involved during bit interval, and that is why it is non-return to 0 level. So, effectively you have got fewer transmissions for data transfer. So, less electromagnetic interference issues would come in, because any transition means what? You generate basically all possible electromagnetic radiations, and there could be interference problems. The moment such transitions are minimized, EMI problems are minimized, but it requires less oscillator drift. Why? Because your bit period has to be strictly monitored, okay? Because if the bit period is lost, if there is an oscillator drift, if the bit period changes, then interpretation of data can become erroneous. So, if you look into the structure, what we are talking about is, say if this is your original bit stream, okay? So, effectively if there are two zeros, there are no transitions in between. So, they are at constant voltage level. I am looking at 0 means low voltage, and ones is the continuous 6. So, continuous 6 ones. So, it is a continuous voltage level. So, since there are no transitions during bit interval, this is non-return to 0. Now, obviously what it requires, there cannot be a clock drift from processing element to processing element. If there is a clock drift, then interpretation of these intervals, bit intervals, can become erroneous. So, instead of counting 6 ones, I may count 5 ones. So, then there will be wrong data. So, how to minimize this problem of clock drift? So, what it uses is bit stuffed stream. What it does is, it uses a convention, and at regular intervals it puts in a opposite bit which is stuffed in, it is put in between. Okay. So, what we will see here is that here instead of continuous 6 bits, what you have got, there is 5 ones, and there is a 1 0 bit has been stuffed in, so that the clock can be synchronized if required, because these transitions have to be noted. Similarly, there would be opposite bit stuffed in case of continuous zeros. So, effectively what your CAN uses it non-return to 0 and bit stuffing to prevent the problem of clock drifting, and wrong interpretation of bit interval. Typically, the feature is that if you look at the baud rate, so up to 40 meters, it can work at typically 1 Mbps as a baud rate. So, this is typically the characteristics of a CAN. So, 40 meters, what you can realize that if you are looking at an appliances like car or any such device, this 40 meter is good enough. And so, I can have a high speed data transfer inside an application like car. This is the basic message format. In fact, this format basically is what? It gives you the features of data link layer, not just a physical layer. So, there is a data frame. So, you have got typically start of frame, this arbitration field, control field, data field, CRC field to take care of an error, error check, acknowledgement, and there is an end of frame. This is a typical CAN message format. So, arbitration field actually consists of what is called the identifier and RTR bit. In fact, RTR bit indicates whether it is a data request frame or actually a data frame. The identifier's length is 11 bits, and there is another version which has got 29 bits for extended frame. And in fact, this encodes also the priority. This 11 bits also encodes a priority. So, lower value implies higher priority for this field, and this will be very interestingly exploited for arbitration. The control field consists of 6 bits, includes data length code and 2 bits reserved for expansion. Data length code tells you how many data bytes are part of this message, and data field contains actually the data bytes, and there can be maximum of 8 such bytes. CSC field is there, acknowledge field, there is end of frame, and each data frame and remote frame is actually a request for the data frame, is delimited by a flag sequence consisting of 7 recessive bits, okay, 7 bits to, which one is a recessive bit in this case? In this case, high would be the recessive bit because 0 is active. So, 7 recessive bits would be put in to separate out the individual data frames, okay. Why this is required? Because next frame transmission has to start again at the end of this recessive period. So, that is what is for separating the message frames. Now we come to the arbitration mechanism. In fact, CAN is a multi-master network, and what we say that it uses carrier sense multiple access collision detection with arbitration on message priority. This is a basic protocol, CSMS CD plus AMP, okay, and this AMP basically distinguishes this network from your well known Ethernet. Now, all network nodes transmit synchronously. So, all nodes start sending their identifier fields at the same time, okay, it is a synchronous at the same time. So, when a node hears a dominant bit in the identifier, when it tries to send recessive bit, it stops transmitting, okay. So, it stops transmitting, letting the other node with a higher priority message continue uninterrupted, okay, and this becomes automatically resolved with regard to the priority. Why? Because the lower value will have higher priority. So, if you have a 0 over there, that is a dominant bit. So, obviously, the dominant bit will be taken precedence over the recessive bit. So, if I have a message with a higher priority, that message will be transmitted. So, the collision gets automatically resolved on the basis of message priority, okay. This is something which is very, very interesting with CAN. So, two nodes on the network are therefore not allowed to send messages also with the same ID. This is another issue, because these identifiers are what? Identifiers are not linked with the node, identifiers linked with the meaning of the message, okay. So, if the two nodes tries to associate the same identifier value, then also there is a problem. So, the arbitration mechanism needs to address this problem as well. If two nodes try to send a message with the same ID at the same time, obviously arbitration will not work. So, one of the transmitting nodes will detect that his message is distorted outside of the arbitration field, because since they are sitting on the bus, they can listen to the data that it is sending as well, okay. The nodes will then use error handling of CAN, which in this case ultimately will lead to one of the transmitting node being switched off. Okay, because these error can only be detected by the transmitting node only, because since it is connected on the same bus and each node is listening to whatever data is being put on the network. So, transmitting node can find out that the data it is sending is not the data that it is receiving. Why? Because here also the 0 bit will be dominant bit. If the other node is sending a 0 outside the identifier field, then the transmitting node will detect an error, and that error has to be handled through CAN error control mechanism. The remote frames are basically used for request of information. So, a frame with the RTR bit set means the transmitting node is asking for information of a particular type given by the identifier. Okay, identifier indicates a data type. And node which has the information available should then respond by sending information onto the network. So, this is also very interesting. When a data is being asked for, it is not being asked for with a node address, it is being asked for with the type information. So, the nodes which have the data of a particular type can respond automatically. Depending on the implementation of the CAN controller, the answer may be sent automatically. So, typically this would look like this. It does not have a data frame, it has got a control field, it has got the arbitration field which is your identifier field and your acknowledgement field. So, this is your RTR, this is RTF, the remote transfer frame. Here you really do not have the data field. This is the only basic difference that you have got. The next interesting feature is error control, because all data link layer protocols are expected to provide some kind of error management. The error detection, signaling and fault confinement defined in the CAN standard makes a CAN bus very reliable, and this is a very typical of data link layer functionality. The built-in error detection of the controllers together with error signaling makes sure that the information is correct and consistent, and faulty nodes will go to modes where they do not disturb the traffic on the bus. This is also a very important issue, because that node, because they are all listening onto the bus, a node if it has become faulty, that needs to be isolated to maintain the correct use of the remaining part of the network. So, what is the error process? So, error is detected by the CAN controller, which can function as a transmitter or as a receiver. Whenever it detects an error frame is immediately transmitted, and the message is cancelled at all nodes, any message which is being transmitted, and status is updated, and then the message is retransmitted. If several controllers have messages to send, normal arbitration is used. So, try to understand scenario. Scenario is the moment a CAN controller detects an error, it sends an error frame, which is a third type of frame. We have looked at basically data frame, we have looked at remote data request frame, now it is an error frame. So, when an error frame goes in, none of the messages are transmitted. Okay? So, messages, all nodes refrain from sending the messages. After some time the message is retransmitted, and when the message is retransmitted, normal arbitration scheme is followed. So, what kind of errors can occur? Because this error detection is done by the CAN controller. There could be two kinds of errors, what we say bit errors and the message errors. Bit errors is typically a bit stuffing error. I have already shown you the bit stuffing format. A receiving node that detects violation, that is, you have got more than 5 consecutive ones or more than 5 consecutive zeros, will see a bit stuffing violation, and it would flag that error. Okay? So, that means randomly some bit change has taken place. And a bit error is what? A transmitting node always reads back the message as it is sending. Okay? If it detects a different bit value on the bus than it sent, then the bit is not part of the arbitration, and the bit is not part of the arbitration field or in the acknowledgement field, then the error is detected. Okay? So, that means that error which is now on the bus has been changed for some reason. So, that error can be detected by the transmitting node only. Once it detects that error, it can flag that error as well. then there will be message errors, because you already have the error correction code as part of the message frame. So, using that error can be detected, checksum error. And frame error is with respect to some of the predefined bits, and if receiver detects an invalid bit in one of these positions, a form error will be flagged. And if a transmitter determines that a message has not been acknowledged, now this is very, very important. If a transmitter determines that message has not been acknowledged, then an ACK error is flagged, okay, because there is a provision for, if you see, I have given a provision for an acknowledgement bit. That acknowledgement bit has to arrive. If it has not arrived, then transmitter will flag an error, okay. So, transmitter may decide to retransmit the message because it has not been acknowledged. So, on the basis of these errors, that CAN controller can be in variety of modes: error active, error passive, pass off. Now, this is an active error flag. Messages can be received and transmitted, and on detecting an error, an active error flag is sent, because this is a normal mode of operation. If there is an error, it will just set an active error flag. What is a passive error? This mode is entered when controller has frequent problems. And if there is this problem on detecting an error while receiving, a passive error flag is sent, okay. And you will see that how these two flags are different and how that helps in error management. Pass off is entered if the controller has serious problems with transmitting messages. So, no messages can be received or transmitted until the CAN controller is reset by the host microcontroller or processor, or even manually. So, this is completely off the bus. So, when an error is detected, it sends an error flag on the bus, okay, that is the error frame. This prevents any other node from accepting the message and ensures consistency of data throughout the network, okay. So, if the message is already there and if it receives an error flag, that message would be actually rejected if the message is being transmitted. The active error flag consists of 6 low bits and is used if the node transmitting the error frame is in active error state. What does that mean? These low bits would be the dominant bits, okay. So, as low is dominant, all other nodes will detect bit stuffing violation and send their own error flags, okay, because this is 6 low bits. So, it is violating the bit stuff requirement. You cannot have. So, once it detects that error, they will send their own error flags, okay. After this, the nodes that want to transmitting will start to do so. So, that means the data is basically being removed. All of these nodes will flag errors. So, just please note how the error is being managed. Whenever an active error flag is transmitted, that will be indicated by what? Will be indicated by a transmitting node, say for example, when it detects an error, and then these 6 low bits, if it is sent, what will happen? They are the dominant bits. So, the receiving nodes will indicate a bit error and that will raise again the error flag. So, all the nodes will be now realizing that there is an error in the bus, and therefore, they would ignore the data. At the next instance, because it is a synchronous bus, so the next instant will arrive for the transmission of the frame, then the retransmission can take place. There is also a passive error mode of the CAN controller. So, in this case, error flag only consists of passive bits. So, bus is not affected. So, if no other node detected an error, the message will be sent uninterrupted. This ensures that a node having problems with receiving cannot block the bus. This is something which is very, very important. A node may find it is getting into repeated error. This is because, why, if you remember, when a node goes into passive error mode, when there are more frequent errors and when it is not in a normal mode of operation. So, that means the error that it is detecting may be because of the malfunctioning of the controller, CAN controller at that node itself. So, effectively what it is pushing now? It is pushing 6 passive bits, and these bits will not modify the data on the bus because low bit is dominant bit. Is this clear? So, data transmission will take place without any interruption. Only the current node will be unable to receive the data. And since you are sending any kind of request or a data with identifier which is not linked to the node but linked to the meaning of the data, there may be other node which may satisfy your request for the data. Okay, that's how the complete operation can go on even because of a failure of a single node. Is this clear? So, this advanced error handling makes CAN a very attractive protocol for these kind of embedded, networked embedded applications, where we are using it say in a car, in an industrial situation, as well as even in medical equipments. Okay. So, the error frame looks something like this. So, here is the error flag, and this is the error flag which is transmitted, okay, which is transmitted once the error is detected by the corresponding transmitter or the receiver. So, basic CAN controller looks something like this. So, this is your main controller. What is this main controller? Main controller would be actually your microcontroller or an ASIC. This is basically the CAN controller, additional hardware, which also has a software to implement this protocol. So, what is interesting here is that you have got a status and control registers, transmit buffer and a receive buffer, and the CAN protocol controller which will implement what is called an acceptance filtering. This protocol controller examines what? The identifier field. So, what we say, the interesting messages are filtered out by using two registers that operate on the message identifier, because that value would be loaded onto this register of the protocol CAN control identifier. So, a simple conceptual model could be if this CAN controller is configured with a microcontroller for a particular task, then this microcontroller would load a particular value to that register. So, the protocol controller will do what? Will check for that particular value in the identifier field of the CAN message. If that value message, if these two values matches, then what it will do? Then it is stored in one of the receive buffers. There can be multiple such receive buffers. If there is a match between the value loaded in that register with that of the identifier field of the frame being received, then the data part of that frame is stored in the receive buffer, and from receive buffer it will get transferred to the main controller for processing. Now, there can be higher layer protocols built on top of this basic physical layer and the data link layer. So, these higher level protocols can define what are called startup behavior, definition of message identifiers for different nodes, because who defines this message identifiers? Okay, because message identifiers, the protocol says that many bits are reserved for this, but what is the meaning of these identifiers? That has to be defined through a higher level protocol. Then definition of contents of data frames, also the flow control, because if you need transmutation of messages greater than 8 bytes, there has to be a flow control mechanism implemented. That comes a part of a higher layer protocols. So, these are some of the features which the higher layer protocol should implement when an application is being implemented around CAN. And there are some protocols which are available, say CAN open, device nets. These are also protocols developed by this kind of vendor associations. This is again a specification from automobile engineers for targeted for heavy vehicle application, SAE J1939. This is an automobile association specifications. So, the applications are many, okay. In fact, building automation, food distribution appliances, transportation, production, medical, agriculture and harvester machines. So, you will find that interesting thing is that all these applications are with regard to the devices which are to be used in a variety of scenarios, situations, and which are not necessarily a very kind of a laboratory controlled conditions. Okay. So, that is why this error control feature of CAN becomes something of importance. An example is this a caterpillar, this earth mover, this has got 195 sensors, in fact an actuators plus wireless data link in such a vehicle. Just look at the number of processing elements and sensors being going into a heavy vehicle, okay, and the need for therefore networking protocols, a pretty sophisticated physical and data link networking protocol to manage all these sensors and processing elements in such a kind of a vehicle. Even if you see that your automated drilling vehicles which are used for oil explorations and others, they are also the various kinds of components are used with sensors and processing elements, and they also needs to be networked, and CAN is a protocol which is used for those purposes as well. So, this brings us to the end of today's lecture. So, what we have understood, obviously the concept of networked embedded system through this basic application, and we have studied this protocol which is designed for applications like automobile. So, it is not a general purpose protocol, but it is not that general purpose protocols are also not being used for embedded systems. So, we shall look at use of general purpose protocols in embedded appliances in the next class.